Tonight, you stand in a sun-drenched courtyard. The year is 1725, and you're watching two timepieces disagree with each other like bickering old scholars. To your left, mounted on a stone pedestal, sits a gleaming brass sundial, its gnomon casting a sharp, unwavering shadow across the engraved hours. To your right, inside the cool shadow of a workshop doorway, ticks a tall grandfather clock, its pendulum swinging with the solemn regularity of a heartbeat. You glance at the sundial. It reads 10:30. You step inside and check the clock. The clock reads 15:15. You step back outside, rub your eyes, and check again. The shadow hasn't moved. The clock hasn't stopped. Both instruments appear flawless, yet they cannot agree on what time it is. And here's the dry reality check that lodges in your throat like a breadcrumb. If you were an 18th century clockmaker staking your reputation on this problem, you'd probably go mad before you solved it. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Now, dim the lights, and let's ease into tonight's journey together. You are, right now, experiencing the central obsession of every serious horologist who lived between the late 1600s and the early 1800s. It's an obsession that drove craftsmen to their workbenches before dawn and kept them there long after the candles burned down to stubs. They called it the equation of time, and the name itself is a kind of lie, or at least, a gentle misdirection designed to make an infuriating cosmic prank sound like a neat mathematical problem. The equation of time isn't an equation in the way you might remember from school, with an equals sign and an x to solve. It's a correction. It's the number of minutes you have to add to or subtract from the reading on your sundial to make it match the reading on your clock. And the maddening thing, the thing that kept those clockmakers hunched over their files and gears for decades, is that this correction changes every single day. Think about what that means. Imagine building a clock so precise that its pendulum accounts for temperature changes, so finely geared that its hands sweep the hours without a tremor. You deliver it to a wealthy client, install it in their library, and set it by the sun at noon. A week later, the client summons you back. The clock is wrong. The sundial says one thing, the clock says another, and the client is not amused. You check the mechanism. It's perfect. You check the sundial. It's perfect. And yet, the disagreement persists. This is the nightmare that greeted clockmakers the moment their machines became accurate enough to measure the sun's inconsistency. You might assume, standing there in that courtyard, that the sundial is the simpler instrument and therefore the more reliable one. After all, it has no moving parts. It just sits there, collecting shadow. But the sundial isn't measuring time in the way you understand it. It's measuring the apparent motion of a star across a curved sky. And that star, the sun, is not the steady timekeeper you've always assumed it to be. It's a liar. A beautiful, life-giving, warmth-spreading liar. But a liar nonetheless. Some days, the sun crosses the sky a little faster than usual. Some days, it dawdles. And because the sundial faithfully reports whatever the sun is doing, it ends up telling a version of time that drifts away from the perfectly regular hours your clock is trying to keep. Historians still argue whether the first clockmakers to encounter this problem truly understood its astronomical roots or simply treated it as a gremlin in the workshop. Some of them probably spent weeks adjusting weights, swapping pendulums, and blaming the weather before it dawned on them that the fault wasn't in their machines but in the heavens themselves. And here's a lesser-known detail that might make you snort into your tea. For centuries, sundials often included little tables carved into their faces. Handy little cheat sheets that told you how many minutes to add or subtract on any given day to get clock time. So even the sundial makers knew their instruments were lying. They just didn't see it as a problem. They saw it as a feature of living on a planet that refuses to spin in a neat, orderly circle. You walk back into the workshop, leaving the sundial to its stubborn shadow. The grandfather clock ticks on, oblivious to the argument outside. And somewhere in the back of your mind, a question begins to form. A question that will haunt you through the coming decades. If the sun can't be trusted to keep steady time, then what can? You step back into the courtyard the next morning, and the sundial greets you like an old friend who enjoys watching you squirm. The shadow stretches thin and sharp from the no man's edge, and you notice something you hadn't paid attention to yesterday. The engraved lines on the dial's face aren't spaced evenly. At noon, they are generous and wide. Toward dawn and dusk, they squeeze together like passengers on a crowded coach. This isn't poor craftsmanship. This is geometry. The sundial isn't broken. It's just honest about a truth your clock was designed to hide. The sun moves across the sky at a speed that varies with the seasons, and any instrument that follows the sun must follow its moods. You crouch down and run your finger along one of those uneven hour lines. The brass is warm from the morning light. And you realize, perhaps for the first time, that the sundial's flaw is actually a message. It's telling you that time, as measured by the sun, is elastic. It stretches and compresses. It rushes in January and drags in July. The clock inside the workshop, with its perfectly divided dial and its metronome pendulum, is the real liar here, because it insists that every hour contains exactly the same number of seconds, when the sun itself proves otherwise. This is the deception that 18th-century clockmakers had to swallow before they could even begin to solve the equation of time. They had to accept that their quest for mechanical perfection was, in a sense, a quest to build a machine that would lie more consistently than the sun. They weren't trying to replicate nature. They were trying to correct it. You stand up and watch the shadow creep another fraction of an inch. The sundial doesn't care about your clocks or your equations. It just sits there, doing what it's always done since the first Babylonian priest scratched a line in the dirt. And what it's doing is tracing the consequences of two astronomical facts that no clockmaker could change, no matter how finely they cut their gears. The first fact is that Earth's orbit around the sun isn't a perfect circle. It's an ellipse, a slightly squashed circle, like a trampled wedding ring. And because the orbit is elliptical, Earth doesn't travel at a constant speed. When it's closer to the sun, in early January, it feels the sun's gravitational pull more strongly and speeds up. When it's farther away, in early July, it slows down. This means that the sun, as seen from Earth, appears to drift eastward against the background stars at a rate that changes throughout the year. Some days it moves a little more than 1 degree. Some days, a little less. And since a sundial measures time by that eastward drift, it has no choice but to reflect this cosmic speeding ticket. The second fact is that Earth is tilted on its axis. You know this already. It's why you have seasons. But the tilt also affects how the sun's apparent motion projects onto your flat sundial. Even if Earth's orbit were a perfect circle, the tilt would still cause the sun to trace an uneven path across the sky. It's like shining a flashlight onto a tilted hoop. The spot of light moves faster on some parts of the hoop than others. The tilt, combined with the elliptical orbit, creates a double dose of irregularity that adds up to the equation of time. Historians still argue whether ancient sundial makers understood these causes or just accepted the effects as part of the natural order. But here's a surprising detail that suggests they knew more than you might expect. Some Greek and Roman sundials included curved hour lines, not straight ones. They'd figured out that a simple straight line wouldn't capture the sun's true path across the seasons. They were literally carving the equation of time into stone, centuries before anyone gave it a name. You trace one of those curved lines with your eye, imagining the craftsman who cut it. He probably never owned a clock. He probably never worried about minutes. His world ran on natural rhythms: dawn, noon, dusk. The uneven hours his sundial recorded were perfectly adequate for a farmer, a priest, or a merchant who just needed to know when the market opened. But you're not living in that world anymore. You're standing on the threshold of an age where minutes matter, where ships navigate by the stars and factory whistles blow at precise times. And that means the sundial's honest deception has become a problem you can no longer ignore. You push open the workshop door and the tick of the grandfather clock wraps around you like a familiar rhythm. The pendulum swings back and forth, back and forth. A brass disc on a rod that seems to mock the sun's lazy inconsistency. You run your hand along the clock's mahogany case, feeling the faint vibration of each beat. This is precision. This is regularity. This is what happens when human ingenuity decides to impose order on a chaotic universe. And yet, as you stand here, you know that this beautiful machine is part of the problem, not the solution. Early clockmakers didn't set out to contradict the sun. They set out to replicate it. The first mechanical clocks, built in European monasteries during the late Middle Ages, were literally designed to ring bells at the appointed hours for prayer. They didn't have dials or hands. They just hammered a bell at matins, at vespers, at compline. And for centuries, that was enough. Nobody checked those clocks against a sundial to see if they were accurate to the minute. Nobody cared. The bells rang, the monks prayed, and the world turned. But something changed in the 17th century. It started with Galileo. Or so the story goes. He was sitting in the cathedral at Pisa, watching a chandelier swing back and forth in the breeze, and he noticed something peculiar. No matter how wide or narrow the swing, each oscillation seemed to take the same amount of time. He tested it by timing the swings against his own pulse. A doctor's son, he knew how to count heartbeats, and realized he'd stumbled upon a principle that would change timekeeping forever: the isochronism of the pendulum. You might think this discovery would have solved everything. A pendulum swings at a regular rate, so build a clock around it and you've tamed time. But here's the catch that Galileo never fully worked out. Pendulums aren't perfectly isochronous. They're close. But close isn't good enough when you're trying to measure the sun's subtle variations. A pendulum's period actually depends slightly on the amplitude of its swing, how far it arcs back and forth. As the clock runs and friction slows the swing, the rate changes. And temperature affects the length of the pendulum rod. Metal expands in heat, contracts in cold, and the clock runs slower or faster accordingly. You pick up a brass pendulum bob from the workbench and feel its weight in your palm. It's heavier than you expected. The clockmakers who came after Galileo spent decades wrestling with these complications. They invented gridiron pendulums with alternating brass and steel rods that expanded and contracted in opposite directions, cancelling out temperature errors. They built mercury pendulums where the bob was a glass jar of liquid metal that rose as the rod expanded, keeping the center of mass constant. They chased perfection with an intensity that bordered on obsession. And they got close, incredibly close, to building machines that could keep time to within a second per day. And that's when the trouble really started. Because once your clock is accurate enough to measure the sun's irregularities, you can no longer pretend those irregularities don't exist. A medieval monk with a water clock never noticed the equation of time. His clock drifted by minutes each day anyway. So who could say whether the sun or the clock was at fault? But a 17th century horologist with a pendulum regulator accurate to a few seconds could set his clock by the sun at noon, check it a week later, and find a discrepancy that could not be explained by friction or temperature or any mechanical flaw. The clock was right. The sun was right. And yet they disagreed. Historians still argue whether Christian Huygens, the Dutch scientist who built the first practical pendulum clock in 1656, ever fully grasped the implications of this disagreement. He was a genius. He discovered Saturn's rings, invented the balance spring, laid the foundations of probability theory, but he was also a man of his time, convinced that the universe ran on neat mathematical laws. The idea that the sun itself might be the inconsistent party probably struck him as absurd. And here's a lesser-known detail that reveals just how deep this confusion ran. Some early pendulum clocks actually had 2-minute hands, one that followed the clock's regular beat, and another that could be adjusted by hand to match the sun. The clockmaker was essentially saying, "I've done my part. You deal with the sun." You set the pendulum bob back on the bench and listen to the grandfather clock's steady tick. It's trying so hard to be perfect. It wants to be the reliable heartbeat of a household, the arbiter of mealtimes and appointments and bedtimes. But the sun keeps moving at its own pace, and no amount of mechanical ingenuity can make it march to the pendulum's drum. You leave the workshop and walk through narrow cobblestone streets until you reach a quiet library. Its shelves heavy with leather-bound volumes that smell of age and dust. You pull down a thick manuscript, its pages covered in Latin and diagrams that look like something from another world. The name on the title page is Claudius Ptolemy, and he lived nearly 1500 years before you were born. Yet here, in his Almagest, you find the seeds of the very problem that keeps you awake at night. Ptolemy was an astronomer working in Alexandria, that great Egyptian city where Greek learning met Egyptian antiquity and Roman power. He wasn't trying to build clocks. He was trying to predict the positions of planets, to map the heavens, to understand why some stars wandered while others stayed fixed. But in the course of this work, he stumbled upon a distinction that would haunt clockmakers for millennia: the difference between the mean sun and the true sun. You trace your finger along a diagram showing Earth at the center of the universe. That was Ptolemy's model, the one that would dominate Western thought for over 1,000 years. Around Earth, the sun, moon, and planets moved in complex circles upon circles, epicycles upon deference, a cosmic clockwork of gears made of celestial crystal. And within this intricate machinery, Ptolemy needed a way to calculate time. Not the time you feel passing, but the time you could measure consistently, mathematically, predictably. So he invented the mean sun. The mean sun doesn't exist. You'll never see it in the sky. It's a ghost, a mathematical convenience, our imaginary version of our star that moves at perfectly constant speed along the celestial equator. It never speeds up, never slows down. It just marches steadily, day after day, year after year, completing its circle in exactly the same interval. This is the sun that your grandfather clock wants to follow. This is the sun that lives inside its gears and pendulum. The true sun, on the other hand, is the one you can actually see. It's the blazing disk that rises in the east, arcs across the sky, and sets in the west. It's the one that casts shadows on your sundial. And in Ptolemy's model, as in reality, the true sun does not move at constant speed. Sometimes it's ahead of the mean sun. Sometimes it's behind. The gap between them, the difference between where the true sun is and where the mean sun would be, is the equation of time. You sit back in the creaking wooden chair and let that sink in. A man in Roman Egypt, working by lamplight with nothing but a stick in his eyes and a brain the size of a planet, had already mapped out the conceptual framework that 18th-century clockmakers were still struggling to implement mechanically. Ptolemy even provided tables showing how much the true sun deviated from the mean sun on any given day of the year. He called it the prostapheresis, a mouthful of a Greek word meaning something like addition and subtraction. It was the equation of time in everything but name. Historians still argue whether Ptolemy truly understood these deviations as physical realities or just treated them as mathematical fudge factors to make his models work. He was, after all, trying to save the phenomena, to preserve the appearance of uniform circular motion that Greek philosophy demanded. His epicycles were beautiful fictions, and the mean sun may have been just another fiction, a convenient baseline against which to measure the true sun's wanderings. But here's a detail that suggests he took it more seriously than that. Ptolemy devoted an entire book of the Almagest to the length of the seasons. He'd noticed that spring and summer together lasted a few days longer than autumn and winter, and he knew this meant the sun's apparent motion wasn't uniform. He wasn't just guessing. He was measuring. You close the manuscript and run your hand over its worn leather cover. Ptolemy's universe was wrong. Earth isn't the center. The planets don't move on crystal spheres. But his mean sun survived the Copernican revolution intact. When Nicolaus Copernicus moved the sun to the center, he kept the mean sun as a computational tool. When Johannes Kepler smashed the circles into ellipses, he kept the mean sun. It's still there today, lurking in the equations astronomers used to point their telescopes, a ghost that refuses to be exorcised because it's just too useful. And somewhere in a workshop not far from this library, a clockmaker is filing a brass wheel, trying to make his machine follow the true sun while keeping time with the mean sun. He probably doesn't know he's reenacting a drama first staged in Alexandria 15 centuries ago. He probably doesn't care. He just wants his clock to agree with the sundial, at least once in a while. You step out of the library and the word equation rattles around in your mind like a loose gear. It's a strange word to use for a problem about time. Equations are for algebra, for balancing scales, for finding unknown quantities. But as you walk back toward the workshop, you realize that the clockmakers who inherited this problem were using equation in an older sense, one that had nothing to do with xs and ys and everything to do with correction. In the 17th and 18th centuries, an equation was an adjustment. It was the small amount you added to or subtracted from a reading to make it correct. Navigators applied equations to their sextant readings to account for atmospheric refraction. Astronomers applied equations to their observations to account for the speed of light. And clockmakers applied the equation of time to their sundials to get something that resembled the regular hours their machines kept. The word itself comes from the Latin equatio, meaning equalization. You were making things equal. You were reconciling two things that refused to reconcile themselves. This linguistic detail matters because it reveals something about how people thought about time before the industrial age. They didn't see the sundial as wrong and the clock as right, or vice versa. They saw two different kinds of time, apparent time and mean time, and they needed an equation to bridge them. The sundial showed you where the sun actually was. The clock showed you where the sun would be if it behaved itself. Both were valid. Both were useful. They just weren't the same. You pass a street vendor selling pocket sundials, little brass discs with a string for a gnomon, cheap enough for any traveler to afford. They are marked with the hours, but also with tiny numbers etched around the edge. +14, -16, +3. These are the equations for different dates, scratched into the metal so the owner could correct his sundial reading to something like clock time. Even the cheapest instruments carried this astronomical baggage. And here's where the story gets slightly absurd. While clockmakers were borrowing the word equation from astronomers, astronomers were borrowing the problem from ancient observers who'd noticed the sun's irregularity thousands of years earlier. The Babylonians had records of the varying length of daylight. The Chinese had water clocks that they adjusted seasonally. The Mayans built observatories to track the sun's north-south wanderings. Every civilization that ever looked carefully at the sky eventually noticed that the sun wasn't as reliable as it appeared. They just didn't all call it an equation. You stop at a bookshop and browse the shelves. A thin volume catches your eye. The Equation of Time Explained for Mariners and Gentlemen. Inside, the author, some forgotten mathematician with too much time on his hands, tries to explain why the sun runs fast in December and slow in September. He uses diagrams, tables, and analogies about chariots on curved tracks. It's charming and almost entirely wrong by modern standards, but it represents something important. The equation of time had escaped the cloisters of astronomy and entered popular consciousness. Ordinary people wanted to know why their clocks disagreed with the church tower sundial. They wanted an explanation they could carry in their pocket. Historians still argue whether this popular interest drove the clockmakers' obsession or resulted from it. Did craftsmen spend decades on the equation because customers demanded accurate time? Or did customers demand accurate time because craftsmen kept pointing out that the sundial was wrong? It's a chicken and egg question that probably has no single answer. But here's a lesser-known detail that suggests the relationship was more intimate than you might think. Some 18th-century clocks included a second-minute hand that moved at the sun's irregular pace, driven by a cam shaped like the equation of time. You could look at the clock and see both times at once. The steady beat of the mean sun and the lurching dance of the true sun, side by side on the same dial. It was like having a conversation between Ptolemy and your grandfather. You buy the little book and slip it into your pocket. The word equation will never sound quite the same to you again. It's not just math. It's a confession that the universe doesn't line up the way we want it to, and that our finest machines are really just elaborate apologies for that inconvenient truth. You walk out of the bookshop and the afternoon sun warms your face, but your mind is still back in the Middle Ages, following a Benedictine monk through the cloisters of some distant abbey. His name is lost to history. Maybe it was Peter, maybe John, maybe something unpronounceable in Latin. But his work survives in a crumbling manuscript tucked away in a monastic library you'll never visit. He was a timekeeper, not in the modern sense, but in the ancient sense. He needed to know when to pray. The divine office, the cycle of prayers that structured monastic life, demanded precision. Matins before dawn, lauds at daybreak, vespers at sunset, and 7 others scattered through the day and night. A monk who prayed at the wrong hour wasn't just confused. He was spiritually adrift, out of sync with the universal chorus of prayer that rose from monasteries across Christendom. And so the task of keeping time fell to a designated brother, the custos horologiae, the keeper of the clock. Except there was no clock. Not in the way you understand it. There were water clocks, yes, clepsydras that measured time by the drip of water through a small hole. There were candle clocks, marked with hours that burned away as the flame descended. There were even crude mechanical alarms, driven by weights, that could ring a bell at a set hour. But none of these were accurate enough to track the sun's changing schedule through the seasons. So the keeper of the clock did something simpler. He watched the stars. You stand in the abbey courtyard in your imagination, wrapped in a woolen cloak against the night chill. Above you, the stars will slowly across the black dome. The monk beside you points to a bright one, maybe Sirius, maybe Arcturus, and tells you that when it reaches a certain point above the rooftops, it's time for matins. He's not guessing. His following tables he copied by hand from older manuscripts, tables that tell him which stars rise and set at which hours on which nights. He's using the sky as his clock. And here's where the equation of time sneaks into his world, whether he knows it or not. The stars are steady. They rise and set with a regularity that the sun cannot match, because they are so far away that Earth's elliptical orbit doesn't affect their apparent motion. A sidereal day, a day measured by the stars, is almost perfectly constant. So when the monk tracks the stars to set his prayer times, he's actually using mean time without realizing it. He's following the ghost of Ptolemy's mean sun, translated into starlight. But when dawn comes, everything shifts. Dawn is defined by the sun, not the stars. And the sun, as you now know, runs on its own schedule. So the interval between the starrise that signals matins and the sunrise that begins Lord's changes throughout the year. The monk's tables have to account for this. They have to tell him, implicitly, how much the sun has drifted relative to the stars since the last time he checked. He's applying an equation of time without ever naming it. You watch him return to his cell and light a candle. On his desk is a stack of parchment covered in numbers. Tables of stellar positions, tables of sunrise times, tables of the length of daylight at different latitudes. He's been compiling these for years, comparing his observations with those in older manuscripts, correcting errors, smoothing inconsistencies. He's not a scientist in the modern sense. He's a monk doing his duty. But his tables will outlive him. They'll be copied, carried to other monasteries, translated, and eventually find their way into the hands of astronomers who are just beginning to ask why the sun refuses to keep pace with the stars. Historians still argue whether these monastic timekeepers contributed directly to the later science of horology or simply created a reservoir of observational data that others would later mine. But here's a detail that suggests they were more sophisticated than you might expect. Some medieval manuscripts include diagrams showing the varying length of daylight throughout the year, plotted as a curve that rises and falls like a gentle hill. It's a graph, essentially, one of the earliest examples of visualizing time's irregularity. The monks weren't just collecting numbers. They were seeing patterns. You blow out the imaginary candle and step back into the 18th century. Where the street vendors are packing up their stalls and the workshop lights are beginning to glow in the gathering dusk. The monks' tables are still there, somewhere, buried in archives, waiting for someone to recognize what they contain. Centuries of evidence that the sun cannot be trusted, scribbled in neat Latin by men who only wanted to prey on time. You're sitting in a quiet study now. The year is 1543. And a book lies open on the table before you. It's called De Revolutionibus Orbium Celestium, on the revolutions of the heavenly spheres. And its author, Nicolaus Copernicus, is dying somewhere far away, perhaps already dead, unaware that his life's work is about to set the world on fire. You turn the pages carefully, aware that you're handling something precious and dangerous. The book proposes something absurd. That Earth moves, that the sun sits at the center, that everything you thought you knew about the cosmos is wrong. For a clockmaker, this is not just astronomy. It's personal. You run your finger along a diagram showing Earth orbiting the sun, and you realize what Copernicus has done. He's taken Ptolemy's mean sun, that mathematical ghost, and given it a physical home. In the old system, the mean sun was just a convenience, a way to calculate time without worrying about epicycles. But in Copernicus's universe, the mean sun is actually the real sun. It's the stationary star at the center of everything. And the true sun, the one you see rising and setting, is just an effect of Earth's motion. The irregularity isn't in the sun at all. It's in you. This reversal of perspective is exactly the kind of thing that keeps philosophers awake at night. But for a clockmaker it has a very practical consequence. If Earth is moving, then your clock is moving with it. Your pendulum swings not in a stationary laboratory but on a planet that spins on its axis and hurtles through space. And the equation of time, that gap between the sun you see and the sun you imagine, is no longer a quirk of celestial mechanics. It's a direct measure of Earth's imperfect orbit. You lean back in the chair and let this sink in. Copernicus didn't set out to help clockmakers. He was trying to restore what he saw as the true beauty of the cosmos, a universe where everything moved in perfect circles around a central fire. But in the process, he made the equation of time more real. more physical, more urgent. If Ptolemy's mean sun was a ghost, Copernicus's mean sun was a flesh and blood star. And the gap between mean and true time was now a gap between where Earth actually was and where it would be if its orbit were a perfect circle. Historians still argue whether Copernicus himself understood this implication. He was a canon of the church, not a clockmaker. His tables of planetary positions were used by astrologers, not horologists. But here's a detail that suggests he was at least aware of the timekeeping angle. In Book 3 of De Revolutionibus, Copernicus includes a lengthy discussion of the length of the year and the precession of the equinoxes. He calculates the difference between the tropical year, measured by the seasons, and the sidereal year, measured by the stars. He's essentially computing the equation of time over very long intervals, even if he never uses that phrase. You turn to another page and find a diagram that looks strangely familiar. It's a sort of figure-8 curve, drawn to explain the sun's apparent motion against the background stars. You've seen something like it before, scratched onto the face of an old sundial. Copernicus is visualizing the same problem that monks observed and that clockmakers will later chase, the sun's annual dance of lateness and earliness, but he's seeing it from the other side. For him, Earth moves and the sun stands still. For you, standing on that moving Earth, the sun appears to trace that figure-8 in the sky. Same curve, different perspective. And here's the twist that makes this whole story slightly absurd. Copernicus was wrong about the perfect circles. He insisted that planets move in combinations of circles because circles were divine and ellipses were ugly. It took Johannes Kepler, a generation later, to smash that beautiful fiction and replace it with something that actually worked. But Copernicus's central insight, that Earth moves, that the sun is the center, survived Kepler's ellipses intact. And with it, the equation of time became not just a problem for sundial makers but a fundamental fact of life on a moving planet. You close the book gently, aware that you're touching history. Somewhere out there, in workshops across Europe, clockmakers are beginning to hear about this new cosmology. Most of them probably don't read Latin. Most of them will never see a copy of De Revolutionibus. But the ideas will trickle down through almanacs and calendars and conversations, and eventually they'll shape the way those craftsmen think about their work. The equation of time is no longer just a correction. It's a confession that you live on a world that spins and wobbles and races around a star, and that your clocks are really just trying to keep up. You step out of the study and into the early 17th century, where a German mathematician named Johannes Kepler is sitting at his desk, surrounded by piles of astronomical observations left by his predecessor, Tycho Brahe. Tycho was the greatest naked-eye observer who ever lived, a nobleman with a metal nose. His real one got sliced off in a duel, who spent decades recording the positions of planets with unprecedented accuracy. And now those observations belong to Kepler, who is trying to make sense of Mars. Mars is the problem. Mars refuses to behave. In Ptolemy's system, with its circles upon circles, Mars's position could be predicted reasonably well, but not perfectly. In Copernicus's system, with its circles upon circles around the sun, Mars still misbehaved. Kepler has been trying for years to fit Mars's orbit to some combination of circular motions, and nothing works. The errors are small but persistent, 8 minutes of arc, about a quarter of the width of your little finger held at arm's length. Most astronomers would have rounded off those 8 minutes and moved on. But Kepler can't. Tycho's observations are too good. Those 8 minutes matter. You watch over Kepler's shoulder as he tries one model after another, each failing in some subtle way. He's exhausted. He's been at this for years, supported by an increasingly impatient Emperor Rudolf II, who probably doesn't care about Mars's orbit but likes having a famous astronomer at his court. And then, In a flash of insight that historians still argue about, Kepler abandons circles entirely. What if the orbit isn't a circle at all? What if it's an oval? What if it's an ellipse? You see him scratch out the diagrams and start over. An ellipse is a squashed circle, defined by two foci instead of one. In Copernicus's system, the Sun was at the center. In Kepler's new model, the Sun is at one focus of the ellipse, and the other focus is empty, just a point in space with nothing there. The planet doesn't move at constant speed. It speeds up as it approaches the Sun, slows down as it moves away. And this variation in speed, combined with the elliptical path, produces exactly the observed positions of Mars. The 8 minutes of error vanish. For a clockmaker, Kepler's ellipses are both a relief and a nightmare. The relief is that the problem finally has a physical explanation. The Sun's apparent irregularity isn't a flaw in creation or a leftover epicycle. It's a direct consequence of Earth's elliptical orbit and its changing speed. The nightmare is that this explanation is mathematically messy. You can't capture an ellipse with simple gears. You can't make a pendulum follow Kepler's laws. The equation of time is now revealed as the sum of two effects, one from the orbit's shape, the equation of center, and one from the tilt, the equation of the equinoxes. It's a two-bodied beast, and taming it will require all the ingenuity clockmakers can muster. You watch Kepler publish his discoveries in 1609's Astronomia Nova, the new astronomy, and again in 1619's Harmonics Mundi, the harmony of the world. He's not writing for clockmakers. He's writing for mathematicians and astronomers, people who think in terms of geometry and celestial harmonies. But embedded in his work is a gift for anyone trying to build a better clock. A precise description of how the Sun's apparent motion deviates from uniformity, day by day, throughout the year. Here's a lesser-known detail that might make you smile. Kepler almost missed the ellipse entirely. For years he tried to fit Mars's orbit to a curve called an ovoid, an egg shape, because he thought ellipses were too simple, too obvious, too unworthy of the divine creator. It was only when the ovoid failed that he reluctantly tried the ellipse and found it worked perfectly. He later wrote that he felt like a conqueror, but you wonder if he also felt a little foolish for taking the long way around. You step back from Kepler's desk and watch him lean back in his chair, staring at the diagrams that have consumed his life for a decade. He doesn't know it yet, but his ellipses will become the foundation for everything that follows. Isaac Newton will use them to derive the law of gravity. Edmund Halley will use them to predict a comet's return. And clockmakers, struggling to make their machines agree with the Sun, will eventually realize that they are not just fighting friction and temperature and imperfect gears. They are fighting Kepler's ellipses, the shape of Earth's path through space, inscribed in the motion of every shadow. You're standing at a workbench now. The year is 1670, and in front of you lies a brass plate covered in finely engraved lines. It's the dial of a precision clock, not yet assembled, and on its surface you see two separate scales for the minutes. One is evenly divided, 60 equal parts around the circle. The other is uneven, some gaps wider, some narrower, and it takes you a moment to realize what you're looking at. This clock will have 2-minute hands. One will follow the steady beat of the mean sun. The other will follow the true sun's irregular pace, driven by a cam shaped to match the equation of time. And that cam, that little kidney-shaped piece of metal, must account for not one but two separate astronomical effects. The first effect you already know, Earth's elliptical orbit, Kepler's great discovery, which makes the planet speed up and slow down as it circles the Sun. Astronomers call this the equation of center, and it alone would produce an equation of time with a single peak and trough each year. The Sun would run fast for half the year, slow for the other half. and the graph of its deviation would look like a gentle wave. But that's not what the sundials show. The actual equation of time has 4 peaks and troughs, a complicated rhythm that can't come from a single cause. The second effect is Earth's tilt. You know it as the reason for seasons, the 23.5-degree lean that gives you summer and winter. But the tilt also affects how the sun's motion projects onto your clock. Imagine the sun moving along the ecliptic, the path it appears to trace through the constellations, which is tilted relative to the celestial equator. Your clock, like your sundial, measures time by the sun's motion along that equator, not along the ecliptic. And because the 2 circles are tilted, a uniform motion along the ecliptic translates into a non-uniform motion along the equator. Even if Earth's orbit were a perfect circle, the tilt would still make the sun appear to run fast at some times of year and slow at others. You pick up a brass weight from the bench and turn it over in your hands. The tilt effect, called the equation of the equinoxes by astronomers, produces its own wave of fast and slow, with 2 peaks and troughs per year. And when you combine it with the elliptical effect, also 2 peaks and troughs, but at different times and with different amplitudes, you get a composite curve that looks like a lopsided figure 8. This is the analemma, the shape you sometimes see printed on globes or engraved on sundials, the visual representation of the equation of time. Historians still argue whether 17th-century clockmakers fully understood this combination of effects or simply copied the equation from astronomical tables without worrying about its causes. But here's a detail that suggests some of them grasped the geometry quite deeply. A few surviving equation clocks from this period have cams that are cut not to match a simple table but to follow a mathematical curve, the actual sum of 2 sine waves. Someone at that workbench knew enough trigonometry to translate Kepler's ellipses and Earth's tilt into a shape that could be filed into brass. You imagine that clockmaker, hunched over his work, carefully transferring points from a paper graph onto a metal blank. He's probably never read Kepler's books. They're in Latin, expensive, and full of mathematics that would make your eyes cross. But he has access to almanacs that publish the equation of time for each day of the year. He can take those numbers, plot them on a circle, and connect the dots to get the shape of his cam. He doesn't need to know why the sun misbehaves. He just needs to know how much. And yet, somewhere in the back of his mind, he must wonder. The curve his filing has 2 humps, not 1. It peaks in February and November, troughs in May and July. It's too complicated to be accidental. The sun isn't just running fast or slow in a simple rhythm. It's dancing to a tune with 2 instruments, one playing the ellipse, the other playing the tilt. And the combination produces a music that changes every single day. You set the brass weight down and look out the workshop window at the sky. The sun is low, casting long shadows, and you realize that every shadow you've ever seen has been shaped by these 2 effects. The gnomons shadow on a sundial is always telling you the true sun's time. But the true sun's time is always a duet between Kepler and the tilt. No wonder clockmakers spent decades obsessed with this problem. They weren't just fighting mechanical imperfections. They were fighting the very geometry of Earth's motion through space. You walk over to a globe in the corner of the workshop, the kind that wealthy merchants buy to track shipping routes and impress their guests. It's covered in countries and constellations, but your eye is drawn to a small figure-8 curve printed in the Pacific Ocean, somewhere west of South America. It looks like a skinny infinity symbol, one loop larger than the other, with months printed along its length. This is the analemma, the same curve that Kepler might have drawn, the same shape that clockmakers file into their equation cams, the same pattern that the sun itself traces in the sky if you photograph it at the same time each day for a year. You run your finger along the curve. January is at the bottom of the larger loop, July at the top of the smaller one. April and August sit where the curve crosses itself. And along this skinny figure 8, You can read the equation of time directly. How many minutes fast or slow the true sun is on any given day. It's a map of the sun's personality, a portrait of its annual mood swings. The analemma is one of those things that seems simple once you understand it, but getting to that understanding took centuries. The ancient Greeks noticed that the sun's noontime height varied throughout the year, and they could have plotted that variation as a curve. But they didn't have the concept of mean time, so they had no reason to connect that curve to the equation. The medieval monks who graphed the length of daylight were getting close, but they were still thinking in terms of hours and minutes, not in terms of the gap between two different kinds of sun. It was probably 17th century astronomers who first drew the analemma in its modern form. They needed a way to visualize the combined effect of the ellipse and the tilt, and a curve on a globe was the natural solution. You could look at it and see at a glance that the sun runs fastest in early November and slowest in mid-February. You could see that the equation of time is 04 times a year, around April 15th, June 13th, September 1st, and December 25th. You could see that the largest corrections, more than 16 minutes, happen in November and February. For a clockmaker, the analemma was both a tool and a taunt. A tool because it gave you a visual check on your calculations. A taunt because it reminded you that the problem you were trying to solve was fundamentally geometric, not mechanical. No matter how perfectly you cut your gears, no matter how accurately you compensated for temperature and friction, you still had to deal with that figure 8. It was built into the solar system. You pick up a brass analemma plate from the workbench, the kind that might be mounted on a sundial or a precision clock. The figure 8 is engraved with fine lines, each month labeled, each minute of correction marked along the curve. You can see that the loop for December and January is larger than the loop for June and July, reflecting the fact that Earth is closer to the sun in northern winter and moving faster. The asymmetry is a direct consequence of Kepler's ellipses, carved into metal for anyone to see. Historians still argue whether the analemma was first drawn for astronomical or horological purposes. Did sundial makers invent it to help their customers correct the readings? Or did astronomers invent it to understand the sun's motion, and clockmakers borrow it later? The evidence is murky, but here's a detail that suggests the answer might be both. Some of the earliest surviving analemma diagrams appear in books about sundial construction, written for craftsmen who needed practical rules, not theoretical explanations. The curve was useful before it was fully understood. You turn the plate over and see the signature of the craftsman who made it, a name you don't recognize, but someone who spent hours at this bench, filing and polishing, checking and rechecking. He probably didn't think of himself as an astronomer. He thought of himself as a clockmaker who happened to need a particular curve. But his analemma plate, if it survives, will carry the shape of Earth's orbit and the angle of its tilt into future centuries, long after he's forgotten. It's a message from the solar system, engraved in brass by human hands. You set the plate down and look at the globe again. The analemma sits there in the Pacific, patient and unchanging, waiting for anyone who cares to read its story. And somewhere in that story is the answer to why clockmakers spent decades obsessed with the equation of time. They weren't just chasing accuracy. They were chasing the shape of Earth's journey around the sun, trying to capture it in gears and springs, trying to make their machines sing in harmony with the solar system's ancient, elliptical dance. You find yourself on the deck of a ship now. The year is 1764, and the Atlantic stretches to every horizon like a wrinkled gray blanket. The ship rolls gently beneath your feet, and in your hand you hold a marine chronometer, a watch unlike any other, designed to keep accurate time at sea despite the pitching deck, the salt spray, the changes in temperature. This instrument, if it works, could solve the greatest scientific problem of the age: how to find longitude. You know the basics already. Latitude is easy. Measure the height of the sun at noon, consult your tables, and you know how far north or south you are. But longitude requires knowing the time at some reference point, usually Greenwich or Paris, while you're thousands of miles away. If you know that the sun should be overhead at Greenwich at noon, but your local noon occurs at 1:15 by your Greenwich clock, then you're 15 degrees west of Greenwich. Simple in theory, impossible in practice, because no clock had ever survived a long sea voyage with enough accuracy to make the method work. The British government, through the Board of Longitude, had offered a prize of £20,000, a fortune, for a practical solution. Astronomers favored the method of lunar distances, using the moon's motion as a celestial clock. But a carpenter from Yorkshire named John Harrison believed in clocks. He spent decades building larger and larger marine timekeepers, each more accurate than the last, fighting skepticism from the scientific establishment and the board's astronomers. And at the heart of his struggle, lurking in every sea trial, was the equation of time. You look at the chronometer in your hand, not Harrison's original, which is too valuable to risk at sea, but a copy made by one of the craftsmen who followed him. The dial shows hours and minutes and seconds, but also a small subsidiary dial marked equation. This tells you how much to add or subtract from the chronometer's reading to get apparent solar time, the time you need for comparing to local noon. Because even if your chronometer keeps perfect mean time, the sun doesn't. And if you forget the equation, your longitude will be off by up to 1/4 of a degree, enough to miss an island or hit a reef. You imagine Harrison testing his first sea clock, the H1, on a voyage to Lisbon in 1736. He had to explain to the captain why his clock, set by the sun before departure, now disagreed with the sun at sea. Was the clock faulty? Or was the sun being its usual unreliable self? Harrison knew the answer, because he'd spent years studying the equation tables. He could correct for the sun's irregularity and prove that his clock was keeping steady time, even when the sundial said otherwise. The equation of time was his silent partner, his invisible ally, the correction that made his clocks look good. Historians still argue whether Harrison fully understood the astronomy behind the equation or simply used tables compiled by others. He was a craftsman, not a scholar, and his writings are practical rather than theoretical. But here's a detail that suggests he grasped the problem deeply. His later clocks included a special adjustment that allowed them to run on sighted time for astronomical observations, switching back to mean time for navigation. He was comfortable moving between different time scales, different definitions of now, in a way that few of his contemporaries could match. You watch the ship's captain take a noon sight with his sextant, measuring the sun's height as it reaches its peak. He calls out the reading, and you note the time on the chronometer, 2:17 and 34 seconds. But you know that the equation of time for today is -4 minutes and 12 seconds. So the true solar time at Greenwich, the time you need for your longitude calculation, is actually 2:13 and 22 seconds. Local noon is now. The difference is 2 hours, 13 minutes, 22 seconds. At 15 degrees per hour, that's 33 degrees, 21 minutes west of Greenwich. You have your longitude. It works. It actually works. And it works because someone, somewhere, spent decades compiling tables of the equation of time, checking them against observations, printing them in almanacs that sailors could carry to sea. The equation had left the clockmaker's workshop and gone to sea, becoming as essential as the sextant and the compass. Without it, Harrison's chronometers would have been useless. With it, they transformed navigation. You look out at the horizon, imagining all the ships that will soon carry chronometers and equation tables, merchant vessels, naval frigates, exploration ships bound for Pacific islands no European has ever seen. The equation of time will be there for every voyage, a ghost at the navigator's elbow, correcting the sun's lies, making the world smaller and safer and more connected. It never claimed the glory. The chronometer got the prize, the fame, the place in history. But the equation was the quiet partner, the correction that made it all possible. You're back in a workshop now, but this one is different from the others. It's smaller, more intimate, filled with the smell of brass filings and oil. The clockmaker at the bench doesn't look up as you enter. His attention is fixed on a small piece of metal held in a vise, and he's moving a file across its edge with strokes so delicate they barely seem to remove any material at all. You step closer and see what he's making. A kidney-shaped cam, the heart of an equation clock, the physical embodiment of the figure 8 you saw on the globe. This is where the obsession becomes tangible. The equation of time, for all its astronomical grandeur, has to be translated into metal if a clock is to follow it. And the translation happens here, at this bench, through a process that combines mathematics, craftsmanship, and a kind of sculptural intuition that can't be taught from books. You watch as the clockmaker consults a sheet of paper covered in numbers. It's a table of the equation for every day of the year, copied from an almanac, each entry telling him how many minutes fast or slow the true sun runs on that date. He's converting those numbers into angles, so many degrees of rotation for the cam, so many minutes of deviation for the hand. Then he's transferring those angles onto a brass disc, marking points around its circumference that correspond to each day. And finally, he's connecting those points with a smooth curve, filing away the metal outside the curve until only the cam remains. It's tedious work. One mistake, one slip of the file, and the cam is ruined. The clock's equation hand will show the wrong correction, and the whole point of the instrument, to show both mean and true time side by side, is lost. So he works slowly, checking and rechecking, holding the cam up to the light to see if the curve looks right. He's been at this for days, and he'll be at it for days more before the cam is ready to install. You notice that the cam isn't a perfect figure 8. It's more like a lima bean, a lopsided oval with one end fatter than the other. That's because the cam doesn't trace the equation curve directly. It's shaped to move a lever that moves the hand, and the geometry of that linkage transforms the shape. The clockmaker has to account for that transformation, cutting a cam that looks nothing like the analemma but produces exactly the same correction when installed in his machine. Historians still argue whether most clockmakers understood this geometry or simply followed patterns handed down from master to apprentice. The equation clock was a luxury item, expensive and rare, and the knowledge of how to make one was closely guarded. You didn't find instructions in books. You learned by watching, by doing, by ruining a few cams yourself and figuring out where you went wrong. It was a craft secret, passed through generations like a recipe for steel or a formula for clock oil. Here's a detail that reveals just how closely these secrets were held. Some equation clocks from the 18th century have cams that are slightly wrong, off by a minute here, 2 minutes there, but the errors are consistent across multiple clocks made in the same workshop. The master had a template, a master cam that he used to mark others, and that template had small errors built in. His students copied the errors faithfully, never knowing they were wrong, because they'd never seen the original astronomical tables. They were following the recipe, not the science. You watch the clockmaker finish a pass with his file and hold the cam up to the light again. He squints, turns it, sets it back in the vise. Another few strokes, another check. He's chasing a curve that exists only in his mind and on that sheet of paper. A curve that represents the combined effect of Earth's elliptical orbit and its tilted axis, translated through the geometry of his clock into the motion of a brass hand. It's an absurdly indirect way to capture the solar system, but it works. And when the clock is finished, When the cam is installed and the hands are mounted and the pendulum is swinging, anyone who looks at it will see both times at once. The regular minutes of the mean sun, ticking away with mechanical precision, and the irregular minutes of the true sun, lagging and leaping in their annual dance. The equation of time, carved into brass by human hands, running forever in a wooden case. You leave the workshop and travel forward a few decades, to a time when the world is changing faster than anyone expected. The year is 1840, and you're standing in a village square somewhere in the English countryside. There's a sundial on the church tower, old and weathered, casting its shadow across the stone. There's a clock in the tavern, perhaps, or in the home of the wealthiest farmer. And for centuries, that was enough. The village ran on sundial time, adjusted by instinct and tradition, and nobody worried about minutes. But now there's a railway line being built through the valley, and everything is about to change. You walk down to the construction site and watch the navvies laying track, their shovels and picks rising and falling in rhythm. The railway will connect this village to the nearest town, and through that town to the rest of the country. Trains will run on schedules. Schedules require precise times. And precise times require everyone to agree on what time it is. The problem is that every town in England, every village, every farm, runs on its own local time. When the sun is directly overhead in this valley, it's still climbing toward noon in Cornwall and already past noon in London. The difference is only a few minutes, but a few minutes matter when you're trying to catch a train. If your watch says 10 o'clock and the station clock says 10:04, you miss the train. And if the station master sets his clock by the local sundial, and the next station sets theirs by a different sundial, chaos ensues. You watch a railway official walk through the village with a pocket chronometer, comparing it to the church sundial and noting the difference. He's collecting data for the new railway time, which will be based on Greenwich, the mean time at the Royal Observatory, the time that navigators use, the time that ignores the sun's local irregularities. He's explaining to the villagers that they'll need to adjust their clocks, that noon will no longer be when the sun is highest but when the telegraph says it is. They look at him like he's speaking a foreign language. And in a way, he is. The equation of time, which had been an esoteric concern for clockmakers and astronomers, is suddenly a matter of public policy. Every railway timetable has to account for it, at least implicitly, because the sun that rules the village clock is not the sun that rules the railway. The gap between mean time and apparent time, between Greenwich and the village, between the clock in your pocket and the shadow on the tower, that gap is now a source of confusion, missed connections, and occasional disaster. Historians still argue whether the railways caused the adoption of standard time or merely accelerated a trend that was already underway. But here's a detail that suggests the transition was messier than you might think. Some early railway timetables included 2 columns, one for railway time, one for local time, so passengers could figure out when to show up. And some stations had 2 clocks on the platform, one set to Greenwich and one set to the local sundial, side by side like a conversation between the old world and the new. The equation of time was literally displayed on the wall for everyone to see. You imagine a farmer standing on that platform, staring at the 2 clocks, trying to understand why they disagree. He's spent his whole life reading the sun. He knows that noon is when the shadow is shortest, that dawn comes earlier in summer, that the days stretch and shrink with the seasons. Now he's being told that the sun is wrong, that the real time is something called Greenwich Mean Time, that he needs to adjust his watch by a number that changes every day. It's confusing, infuriating, and inevitable. The railways won. By the late 1840s, most British stations were running on Greenwich time. By the 1880s, standard time zones had spread around the world. The equation of time, which had obsessed clockmakers for 2 centuries, became a footnote, a correction that astronomers still used, that sundial enthusiasts still cared about, but that ordinary people could safely ignore. The mean sun had won. The true sun, with its irregular pace and its figure-8 analemma, was retired to the margins. But not entirely. Even today, if you set your watch by a sundial, you'll need the equation. And if you visit that village square, you might still find the old church tower, its shadow creeping across the stones, marking a time that nobody uses anymore. The sun keeps doing what it's always done, indifferent to railways and time zones and the obsessions of clockmakers long dead. You find yourself in a university library now. The year is 1920, and the debate you're about to overhear has been simmering for nearly 2 centuries. Two historians sit across from each other at a long oak table, surrounded by books and manuscripts, and they're arguing about something that seems impossibly arcane. Whether 18th century clockmakers truly understood the astronomy behind the equation of time, or whether they simply followed recipes passed down through generations. The first historian, a man with spectacles and a tweed jacket, believes in the intelligence of craftsmen. He points to the equation clocks themselves, those beautiful machines with their kidney-shaped cams and their dual-minute hands. You can't make something like that, he argues, without understanding what you're doing. The shape of the cam is too precise, too perfectly matched to the astronomical tables. These men knew Kepler. They knew Newton. They just expressed their knowledge in metal instead of words. The second historian, younger and more skeptical, shakes his head. He's spent years reading workshop ledgers and apprentice contracts, and he's found almost no evidence that clockmakers read astronomical books. They learned their trade at the bench, not in the library. They copied cams from templates, not from first principles. They knew that the equation of time existed and that it had a particular value on each day of the year. But they didn't know, and didn't need to know, why. The recipe was enough. You sit down at a nearby table and pretend to read, but you're really listening to their argument unfold. It's a debate about the nature of knowledge itself. Is understanding something the same as being able to do it? Does a clockmaker need to grasp Kepler's ellipses to cut a cam that follows them? Or can he just follow the numbers? And if he follows the numbers without understanding them, is his clock any less accurate? The first historian pulls out a diagram of an equation clock's mechanism, showing how the cam interacts with the lever that drives the equation hand. Look at this, he says. The cam isn't a simple copy of the equation curve. It's transformed by the geometry of the linkage. The clockmaker had to calculate that transformation, had to understand how the lever's length and pivot point would alter the cam's effect. That's not recipe following. That's applied mathematics. The second historian shrugs. Or he learned the shape by trial and error, making cams until one worked, then using that as a template for the rest. Apprentices spent years filing cams under their master's supervision. They didn't need math. They needed patience and a good eye. You realize that both of them are partly right, and that the truth probably lies somewhere in between. Some clockmakers were surely scholars, men who read Newton in translation and corresponded with astronomers. Others were craftsmen pure and simple, inheritors of a tradition that told them what to do without explaining why. And most fell somewhere on the spectrum, knowing more than they could articulate, understanding just enough to solve the problems in front of them. Here's a detail that complicates the debate even further. Some equation clocks have errors that suggest the maker was using a table for the wrong year. The equation of time changes slightly over long periods due to the precession of the equinoxes and other subtle effects. A table printed in 1700 is slightly off by 1750, but many clockmakers kept using the old tables anyway, either because they didn't know better or because they figured a small error was acceptable in a machine that would never be checked against an observatory. They were following the recipe, but the recipe was stale. You watch the two historians pack up their books and leave, still arguing as they walk out the door. The debate will outlive them. It will be picked up by the next generation, and the next, because it touches on something fundamental about how knowledge moves through the world. Does understanding flow from the top down, from astronomers to craftsmen, from theory to practice? Or does it bubble up from below, from the bench to the library, from practical solutions to general principles? The equation of time, which seems like such a narrow problem, opens onto these vast questions. And somewhere, in a museum or a private collection, an 18th century equation clock ticks on, indifferent to the arguments of historians. Its camera rotates, its hands move, its dual-minute hands show both kinds of time side by side. It doesn't know whether its maker understood Kepler. It just does what it was made to do, correcting the sun's lies, keeping the equation alive in brass and steel. You step out of the library and into the present day, or a version of it, at least. The year is now 2024, and you're holding a smartphone in your hand. On its screen is a time display, accurate to within seconds, synchronized automatically with atomic clocks via the internet. You open an app that shows the sun's position, and there it is. A little diagram of the analemma, the figure-8 curve that clockmakers spent centuries trying to capture in metal. The app tells you that today, the equation of time is -6 minutes and 23 seconds. The true sun is behind the mean sun. If you set your watch by a sundial, you'd be late for lunch. The equation of time hasn't gone away. It's still there, still doing its thing, still making the sun run fast in November and slow in February. But you don't need to think about it anymore. Your phone handles it automatically. The atomic clocks that keep global time are adjusted for Earth's irregular rotation, which is a whole different kind of problem. But they don't need to worry about the sun's apparent motion because they don't follow the sun. They follow cesium atoms, which are far more reliable. And yet, the equation lingers. It's in every sundial you've ever seen, even if the maker didn't engrave the correction table. It's in the analemma printed on globes and sometimes on watch dials, a quiet reminder that the sun doesn't march to our drum. It's in the software that controls solar panels, which need to know where the sun will be at any given time to maximize their efficiency. It's in the calculations for satellite orbits and telescope pointing and 100 other technical tasks that most people never think about. You walk through a park and pass a modern sundial, a stainless steel sculpture installed by some civic arts committee. A child is standing beside it, watching the shadow, trying to read the time. Her mother checks her phone and says, "It's about 10 minutes off, sweetheart. You have to add something called the equation of time." The child frowns, confused, and runs off to play. The equation has become a curiosity, a footnote, a thing you explain to children who wonder why the shadow lies. Historians still argue whether the equation of time will ever be completely forgotten, or whether it will survive as one of those esoteric facts that hobbyists keep alive. But here's a detail that suggests it might have a longer tail than you'd expect. Every year, around the equinoxes and solstices, internet searches for equation of time spike. People notice that their sundials are off. They wonder why. They look it up. The old obsession finds new audiences, generation after generation, as long as there are shadows to cast and people to watch them. You sit on a park bench and watch the sun lower toward the horizon. The smartphone in your pocket knows exactly where it is, exactly when it will set, exactly how many minutes of daylight remain. It knows all this without ever looking at the sky. But the sky is still there, the sun still moving, the shadows still creeping across the ground. And somewhere in that shadow is the equation of time, the ghost that clockmakers chased for decades, the correction that made precision possible, the curve that connects Earth's elliptical orbit to every sundial that ever was. The sun sets. The park grows dim. The streetlights flicker on, their timing governed by photocells that respond to actual light, not mean time. For a few minutes, as day becomes night, the true sun and the mean sun are briefly aligned. The equation is zero. The shadow tells the truth. And then the moment passes, the sun dips below the horizon, and the cycle begins again tomorrow. You stand up and walk home through the gathering dusk, leaving the sundial to its silent work. In the morning, someone else will notice that it's wrong. Will wonder why, will maybe look it up. And the equation of time, born in ancient Alexandria, refined by medieval monks, chased by Kepler and Harrison and 1,000 forgotten clockmakers, will do what it's always done. It will correct the sun's lies. It will bridge the gap between the heavens and our machines. It will remind us that time, even now, is not quite what it seems. As you settle into the quiet of the evening, let the rhythm of those ticking clocks fade into the background. Think of all those craftsmen hunched over their benches, filing their cams, chasing a curve that could never be perfectly caught. They knew something that we sometimes forget, that time is a conversation between the earth and the sun, and that conversation has never been perfectly steady. It speeds up, it slows down, it wanders off the path and finds its way back. And our clocks, for all their precision, are just our side of that ancient dialogue. A human attempt to keep pace with a star that dances to its own music. So tonight, if you happen to glance at a shadow or hear a clock strike the hour, remember the equation. Remember the men who spent their lives trying to capture it. And remember that time, even now, is still telling two stories at once.